Hello everyone, my name is Yuhang Wang, currently a postdoc at TU Delft. It's my great pleasure to share some of our work in progress in the CO2 storage. In this talk, I will focus on discussing the impacts of fractures on the behaviors of the hydrodynamic trapping. Okay, first of all, let's take a look at where we can store the CO2 in the subsurface. It has been well accepted that the subsurface geological media provide many opportunities for the secure storage of CO2. As shown in the picture here, there are many candidates formations. We can inject CO2 into the hydrocarbon fields, saline aquifers, and coal seams. In this work, we are focusing on the storage in deep saline aquifers, which have the greatest potential for the geological storage among different types of reservoirs. So the picture on the right shows a schematic of CO2 migration after being injected into the aquifer. It also illustrates the mechanisms by which CO2 can be trapped in the aquifers. So we have three trapping mechanisms here. They are collectively referred to as hydrodynamic trapping. We will go back to this later and see how we model these trappings in our work. Now let's take a look at the saline aquifer. As it is part of the geological media, it shares similar characteristics to what we have learned in the hydrocarbon field. The most common feature is the heterogeneity. Here we focus on one important feature, that is the fracture. So why are we interested in fractures? Because they often have high contrast properties compared to the neighboring matrix. For example, they may serve as highly conductive flow pathways or act as flow barriers blocking the flow. As such, they have a great impact on the fluid flow and transport. Moreover, as reviewed by many outgroups, the fracture network has complex geometries which makes it challenging to describe and model. So till now, the impact of fractures on the full cycle storage process has not been fully quantified and understood, which becomes the objective of this work. Now, we move to a little bit details of the physical models that we use to describe the trapping. So the first one is the structural trapping. We model it by simply imposing the no flow boundary condition on the top boundary. The second one is the residual trapping. It directly relates to the hysteretic behavior of the constitutive relations. So here we show the permeability curve as an example. The data is extracted from an experiment for sandstone. We observed that the hysteresis effect is pronounced for the non-wetting gas phase, as the primary drainage and the imbibition has different paths. So initially, we follow the primary drainage curve as the CO2 being pumped into the aquifer. If the drainage is interrupted, for example, due to the changes of the driving forces, the process is then transitioned from the drainage to imbibition along the scanning curve, which is created to ensure the transition is continuous. Of course, at different turning points, we have different scanning curves, which resulting in different residual saturation. We have to take care of each cell and make sure the hysteretic behavior is captured accurately. And the last one is a dissolution trapping. This is linked to the solubility of CO2. A lot of experiments have been conducted to collect the solubility data across various conditions. In this work, we follow the equating chemical potential model. Here in the first figure, the dots denote the reference data extracted from the literature, and the curves denote our calculated results. So good agreement is obtained for different salinity scenarios. The molality data is then translated into the solution CO2 gram ratio curves that will be used in the simulation. Okay, the fractures are modeled using the projection-based embedded discrete fracture model, or PEDFM. It allows the rock and fractures to be modeled independently. Therefore, it becomes convenient to discretize the domain even with structure grids. Moreover, this model accounts for the fractures with varying conductivities by modifying the matrix to matrix and matrix to fracture transmissibilities. For more details, please refer to the reference at the bottom. Okay, now we move to the results and analysis. First, we consider a single fracture case and investigate the impact of fracture location, inclination angle, and permeability contrast on the dynamic trapping behavior. Then we consider a complex fracture network which is generated using a statistical approach. So due to the limitation of time, I'm not able to show all the results, so I have picked some representative cases to share with you. The first case, as shown, the fracture is placed near the injection well, and we take a look at the dissolution trapping. So on the right, we show the maps of the solution CO2 brine ratio, which reflects the flow dynamics of the liquid phase. Results from the base case without the fractures are shown on the top. We observe that the conductive fractures are served as pathways that enhance the circulation of brine. And this leads to a higher ratio of dissolution trapping compared to that of the base case. So to examine the development of such enhancement, we depict the streamline distribution of the liquid phase in the left half of the domain at t equals 2 to 2, which means 2 times of the injection period. So as shown in the base case, the liquid phase generates a circulation of flow over the domain. However, the presence of the inclined fracture with the inclination angle given by 30 and 60 degree breaks such circulation by providing a preferential pathway for the upward migration of brine. As a result, a local circulation is formed near the fracture. As for the horizontal fracture, it induces 2 local circulations with opposite directions. In this case, the fracture does not help the brine to flow upward, so we observe that the brine with a high concentration of CO2 accumulates along the bottom boundary. In the second case, the fracture is placed on the right side of the domain, and we take a look at the residual trapping. So from the curves, we see that the presence of the fractures give a higher trapping ratios. What is interesting here is that the curve obtained from the case of 60 degree deviates from the other 2 cases, as it has a relatively steep increase. To get a better understanding, we plot the residual saturation maps before and after the steep increase occurs for all the cases. So here we see that in the case of 0 and 30 degree, the residual trapping map remain relatively unchanged. However, for the 60 degree, the trapped gas becomes visible above the fracture tip at t equals to 6. So the reason is shown in the streamline of the liquid phase. In the case of 60 degree, the outflow of brine via the fracture tip invades the CO2 zone, reduces the gas saturation, and eventually it leads to an increase in the residual saturation. Note that the upward flow of brine also occurs for the rest 2 cases, but the magnitude of the velocity, as indicated by the density of the streamline, is very small, so its impact becomes insignificant. For the last one, we check out a case with a complex fracture geometry. It is clear that the dissolution trapping is enhanced in the case of highly conductive fractures, and also when fractures act as flow barriers, they block the gravity-driven convective transport, and the sinking fingers are just developed in the interval of the fracture networks. So here we see that the resulting trapping curve is consistent with our observations. And this is the saturation maps of the gas phase. We observe that in the case of highly conductive fractures, the horizontal migration of CO2 underneath the top boundary is interrupted by the upward flow of brine from the fracture tips. And this leads to a complex dynamic behavior in terms of the residual trapping, as shown on the right. Okay, from those discussions, we see that the fractures do play a very important role, and we would like to emphasize that the accurate characterization of the fracture geometry and its conductivity is critical for the evaluation of the CO2 storage. So to briefly summarize, the PDFM is incorporated into a compositional model to study the CO2 storage in a full cycle period, and our findings from the single fracture geometry are also observed in a complex fracture network. This indicates the scalability of this study for the field-relevant applications. With that, I would like to thank you for your attention, and I'm looking forward to your questions and comments.